Okay, so after learning ionic bonding, covalent bonding, we're moving on to the last part, which is metallic bonding. So let's do some quick recap first. Okay, the first type of bonding that we have learned so far is ionic bond. Okay, so what is ionic bond? So if you recall ionic compounds, for example, sodium chloride, potassium chloride, they all contain a metallic element and a non-metallic element. Okay, so for example, sodium chloride, I have Na+, I will also have a Cl-. So Na+ is from a metal, sodium, and then Cl- is from a non-metallic element, chlorine. So these two will attract each other because of the strong electrostatic forces of attraction between oppositely charged ions. So I'll have a plus, a positive charge, and a negative charge ion. So together, these cations and anions will form very strong electrostatic forces of attraction and resulting in high melting point and boiling point. So they are existing in solid states. So some examples of ionic compound will be sodium chloride, potassium chloride, iron 2 oxide, so on and so forth. Then the next type of bonding that we have learned is covalent, where we ask ourselves, what about elements such as oxygen, nitrogen, hydrogen? They definitely do not have any metallic elements. So the type of bonding that they have is covalent. Okay, so for example, hydrogen. Okay, hydrogen has one valence electron. Okay, so it is not stable. So what they do is these two will come together to form a hydrogen molecule. So what they do make each other stable is that they share their valence electron. So covalent bond is the sharing of valence electrons between two non-metal atoms. So they cannot give away, okay, to each other. So what they do is they share the valence electrons. Okay, so this is one hydrogen molecule. Okay, one molecule. And then in covalent bonding, we learned that there are two types of covalent molecules. One is simple, one is giant. So some examples of covalent substances will be oxygen, we have nitrogen, or we have two different elements, HCl. All these are covalent substances. So the question is, what about metals such as copper, iron, and aluminium, like pure metals? I don't have any non-metallic elements. So what type of bonding do they have? Okay, so in ionic, we learned that it's metal and non-metal. But this time now, we are only looking at metals only, okay? So the last type of bonding that we're going to learn is metallic bonding. Okay, we will take a look at what is metallic bond. And then we will also take a look at the physical properties of metals. So anything that we have learned so far, we learned the bond. And because of this bond, the type of properties that they have. Okay, so the first one, metallic bond. So the learning objective for this part here is to describe and define what is a metallic bond. So there are various types of metals like sodium, group 1, okay? And then we have group 2, magnesium, and then we have calcium, okay? So from periodic table, if I ask you, what is the formula of sodium? What is the formula of magnesium? Calcium. You will be able to tell me sodium is Na, magnesium is Mg, and calcium is Ca. So sodium, magnesium, calcium, what is their bonding? And the properties that we know of metals. Why are they like that? So metals, okay, for example, all your group 1, they are not stable. Okay, they are not stable. They are very reactive. So what they do is they will lose their valence electrons to form positive charged ions. What do I mean by this? So if you take a look at my sodium electronic structure, okay, my sodium is 281. Okay, so I'll draw the structure of sodium. Okay, so sodium in this case is not stable. So it wants to be stable. Everything that we learn, they want to be stable. They want to achieve the noble gas configuration. So what will happen to the sodium? So this sodium, it will lose one valence electron. So when it loses one valence electron, it will become like this. Okay, so with an electronic structure of 281, it will become 28. Okay, so my question now is, where did the valence electron go? Because there is no longer any non-metallic element to receive it, right? So where did that valence electron, where did it go? Okay, so for metals, what they do is they will lose the valence electron to be stable. Okay, and these valence electrons, they are lost. Okay, they are not received by anyone. They are not received by any element. they are considered delocalized. So what they do is they just move freely around. So if you take a look at this picture here, okay, I have all my cations, okay? And the electrons that they have lost, they just flow around freely. So go back to the previous slide. Okay, I repeat. So my sodium metal is not stable. Okay, it is not stable. So it will lose its valence electron to form a stable sodium cation. So my cation will be drawn like that, same as what we have done in ionic bond. Okay, so it has a positive charge. And this particular electron here, it will just be lost and just float around, or rather swim around in this whole metal element. Okay, so these electrons are delocalized, okay, and they just move freely. Okay, so we call this a lattice of positive ions. Okay, so all the positive ions are stable, and these positive ions are surrounded by a sea of delocalized electrons. So these electrons, they are moving around freely. They surround these positive lattice ions. So this is how it looks like. Okay, so you can see all the orange ball here, they are your cations. Okay, they are all stable. And these electrons, they are just moving around freely. They are delocalized. So this structure, okay, if you take a look at this structure, it is a lattice of positive ions surrounded by a sea of delocalized electrons. And this part is very, very important. Okay, remember how they look like, okay, because it will help you to understand why metals behave how they are behaving now. So metallic bond is the strong electrostatic forces of attraction between the lattice of positive cations and the sea of delocalized electrons. So metal cation is positive, your sea of delocalized electrons is negative. So likewise, plus and minus will have strong electrostatic forces of attraction. I repeat, plus and minus, they will attract each other, and this attraction is what we call strong electrostatic forces of attraction. Okay, so go back to the previous slide. You see that I have my lattice of positive ions, okay, the orange balls, okay, they are held in position. Okay, these positive ions are held in position because of the strong electrostatic forces of attraction between lattice of positive ions and the sea of delocalized electrons. Okay, strong electrostatic forces of attraction between these two. Must always mention the word between. So metallic bonds, they are non-directional. Okay, they are like magnetic forces of attraction. So magnets, right, the forces of attraction is non-directional. Okay, so it's everywhere. Okay, so if you look at this diagram here, all right, my delocalized electron is representing by the black dot here. Okay, it has electrostatic forces of attraction here. Okay, with this ion, it also have with this, so on and so forth. So question will ask, how does metallic bond look like? How does metallic bond look like? Okay, so we always remember that it's a lattice of positive ions. Okay, so sodium will form Na+. So I will draw my positive lattice. Okay, so when they are positive lattice ions, right? Lattice means they are regular shape. So I draw regular shape now and draw a minimum of 9. Okay, so sodium ion is Na+. Now each cation is formed because each sodium atom loses one valence electron. I repeat, each sodium atom loses one valence electron. So I have 9 here, right? I will have a total of 9 valence electrons being lost. So 9 delocalized electrons. So I just draw anywhere. So electron, I represent it by E with a negative charge. E with a negative charge. Okay, so I have drawn a total of 9. So this is my labeled diagram. Okay, so this is my labeled diagram. Metallic bond in sodium. Okay, so I have a positive lattice structure. So this is my lattice. So this is my sea of delocalized electrons. So moving on, try the second one. Okay, without looking at the answer, try drawing the second one, which is a metallic bonding in copper. So copper tends to form a positive lattice of Cu2+. Okay, so try drawing. Each copper atom will form a Cu2+ ion, which means each atom will lose 2 valence electrons. So if I draw a total of 9 atoms here, okay, it will form 9 ions, and 9 times 2 valence electrons will be a total of 18. So my sea of delocalized electrons should contain 18 electrons. So when you're drawing the sea of delocalized electrons, you can draw randomly, but make sure that the number of electrons is correct. Okay, so this is your labeled diagram for copper and the metallic bond in copper metal. Okay, now for part C, same thing. Ask yourself aluminium. Aluminium is found in group 3. Okay, so for aluminium, you want to form a lattice of positive ions. It will be forming a lattice of Al3 plus ions. So likewise, try it without looking at the answer. Now when you're drawing, try to make sure that your positive ions are same shape. Okay. So same thing, each atom will lose 3 valence electrons. So 9 of them will lose a total of 27 electrons. So when you're drawing, do ensure you count the number of electrons. So there are a total of 27 electrons here. So this is the diagram for aluminium metal. Okay, now before we end this learning objective, let's take a look at this quick video which summarizes metallic bond. So from this video, you can see that I have my lattice of positive ions and then the sea of delocalized electrons moving everywhere. Okay, so this is metallic bond. So in this part, we learn about metals, what kind of bonding they have, and let's do a quick recap. What is metallic bond? Okay, pause the video, ask yourself, what is metallic bond? Okay, what is the bonding? What's the forces of attraction between them in the structure? Okay, so metallic bond is the strong electrostatic forces of attraction between the lattice of positive ions and the sea of delocalized electrons. You must have the word sea. You must have the word delocalized. Okay, and you must mention that it's a lattice. Okay, to tell me the structure that is regularly arranged positive ions. Okay, so once we are done, put a tick on the first page of your notes. Okay, the last part of this lesson will be understanding how these physical properties come about. So for metals, okay, we ask ourselves, oh, what do we know about metals? Okay, what properties do they have? Okay, physical properties are something that we can measure. Okay, so things like melting point, boiling point, density, all these are physical property. So I have a few properties here. Okay, then my question is, what is your impression of metals? So when I ask you, melting point, boiling point, high or low? Density, high or low? Can it dissolve in water? Can it conduct electricity? Can it conduct heat? Why is it used to make wires? Okay, so these are the properties that we have seen since primary school, and now we're going to understand why. Why do they have these properties? So for thermal conductivity, we know that they are good conductors of heat. Okay, they can conduct electricity. They are heavy. Melting point, boiling point, they are very high. Okay, and they are not soluble in water. Neither they are soluble in oil. Okay, both water and organic solvent. And metals can be molded into different shapes. So they are very malleable, okay, and they can stretch into very thin wires. Okay, so they are called ductile. So why do they have these properties? So let's take a look first. For melting point, boiling point for metals, we know that high melting point, boiling point. But why? Okay, let's move back and take a look at kinetic particle theory. So for kinetic particle theory, we learn this. Okay, they are all made out of particles, and when they melt and when they heat, they absorb heat from the heat source. So this heat is converted to kinetic energy. So they start to move faster and faster. And when they move faster and faster from the fixed position, okay, they will overcome the forces of attraction between them. So I want you all to link kinetic particle theory and bonding. Link them together. Okay? So when I want to melt the solid, energy is used to overcome the forces of attraction. So my question back to you is, what is the force of attraction in metal? Something that we just learned. What is the force of attraction in metal? So first of all, what are the particles in metals? So what are the particles? I have my lattice, positive ion, and sea of delocalized electrons. So these are my particles. Okay, Whatever we learn in kinetic particle theory is general. Now we are being specific. The particles in this case is my lattice of positive ions and the sea of delocalized electrons. So next, what is the force of attraction holding them together? We mentioned plus and minus. So plus and minus, they will attract each other, right? So these two, they have strong electrostatic forces of attraction. Okay, strong electrostatic forces of attraction between the lattice of positive ions and the sea of delocalized electron. And last part, is this force strong? Yes, right? Because it's called strong electrostatic forces of attraction. So a lot of energy or little amount of energy is required to overcome this force. What do you think? Okay, so strong means I need a lot of energy to overcome. If I need a lot of energy, means my temperature to melt must be high. So that is why the melting point, boiling point of metal is high. So why do they generally have high melting point? Okay, because I have my lattice of positive ions surrounded by this sea of delocalized electrons, okay, moving around freely. And if I want to overcome it, okay, I need a lot of energy. So same question as your ionic and covalent bond. Always ask for structure and bonding. So you must state this too. So the first point is we will look at the structure. So what is the structure of metals? So we mentioned that metals, they have giant lattice structure. Okay, and this giant lattice structure is made up of, okay, positive ions and the sea of delocalized electrons. Okay, so the structure is giant lattice structure, okay, with positive lattice ions, okay, and the sea of delocalized electrons. So together, they're bonding, they're held together in this structure is because of the strong electrostatic forces of attraction. Okay, always mention the word between because you need to state this attraction is between what and what. Okay, so for metals, it's between the positive ions and the sea of delocalized electrons. And because of this structure and bonding, means that it is very strong. Okay, I need a lot of energy to overcome these strong forces, and therefore metals have high melting and boiling point. Okay, the stronger the forces of attraction between positive ions and the sea of delocalized electrons, okay, the higher the melting point and boiling point because more energy is needed to overcome it. However, there are some examples or however, there are some exceptions. So mercury, we know that is liquid at room temperature. And then for group 1 metals, which we will learn subsequently, they have low melting point and boiling point, but only these two. So group 1 metals and mercury are exceptions. So we know that they are insoluble in organic solvent and water. Okay, they don't dissolve and they conduct electricity. Okay, they conduct electricity. So when we talk about electrical conductivity, okay, we always look at this phrase called mobile charge carriers. Okay, they must fulfill two criteria. First criteria is they must be mobile, they must be charged. So take a look at this slide here. Okay, I have embedded this metallic structure for you to see. Now tell me, looking at this structure, is there any particle that is mobile? Okay, the lattice of positive ions and the sea of delocalized electrons. So which one is mobile? Ions or electrons? Then my second question is, this particle that is moving, does it have a charge or is it neutral? Okay, so I hope you have figured out the answer. In this case, my electrons are moving, so they are mobile. And my electrons have a charge. All electrons are negatively charged. Okay, so my electrons in the metals can act as mobile charge carriers. So the delocalized valence electrons, they are mobile charge carriers. Okay, they can move freely and they contain charge to conduct electricity. So that is why they are good conductors of electricity. Okay, likewise, they are good conductors of heat because they have the sea of delocalized electrons. Okay, so when we conduct heat, when we want to heat something up, okay, what will happen is that the atoms that are near the heat source, they will gain heat and then they will start to vibrate faster and faster. So as they vibrate faster and faster, they will cause the neighboring atoms to vibrate as well. So this is how heat is being spread across. So why metals are good conductors of heat? Because this movement, this spreading of vibration can occur very quickly. Okay, and why is that so? Something must be able to move very fast, right? When it's being heated up. And then it can travel to heat, or rather vibrate neighboring particles very quickly. So because of the delocalized electrons. So what happens is that the valence electrons, they gain heat, they start to vibrate faster and faster. And when they vibrate faster and faster, they can travel. Okay, if you see this diagram here, they can travel everywhere. Okay, so they are able to travel and collide with the neighboring electrons and the cations faster than others. Okay, so they can move from one end to another very quickly, collide, and then cause them to also vibrate. So this transfer of energy is happening very quickly in metal. Okay, so let's take a look at this video on how metals and why metals can conduct heat and electricity. So from the video, you can see that when it's being heated up, the sea of delocalized electrons can move very quickly, okay, transferring the vibration. And for conductors of electricity, delocalized electrons, they can move and they can conduct electricity from one end to another. Okay, for density, they are closely packed in a regular arrangement. Okay, so the positive ions are regularly packed, okay, in a lattice structure, and they are hold closely and tightly because of the strong electrostatic forces of attraction between the cations and the sea of delocalized electrons. All right, so they have very high density, okay, and that is why they are heavy, okay, in a given volume. And last part will be malleability and ductility. Malleable means that it can be molded into different shapes, like in the shape of a car, or in the shape of a plane. Okay, and ductility means it can be stretched until it forms tiny and thin strand of wires, okay, and without breaking. All right. So why is it that they can be molded into different shapes? Is of course of the strong electrostatic forces of attraction in all direction between lattice of cations and the sea of delocalized electrons. So if you take a look at this picture here, when the metal is being hammered, the layers here, these positive ions, okay, they will slide. Okay, they will slide across. Okay, so at the start it's a square shape, right? Then when it's being hammered, it will form a bent shape. Okay, maybe like this kind. Okay, so why is it that it will not crack? It will still be metal. It will not shatter into pieces because this yellow portion, okay, this yellow portion is your sea of delocalized electrons. So what they do is they are still surrounding the positive lattice ions. So they are still surrounding it and ensuring that they are still in one piece. They don't break apart into different pieces. And this strong electrostatic forces of attraction is in all directions. Okay, so they will not repel because plus and minus will still attract each other. Okay. So when the force is being applied, these layers will slide over each other because they are regularly arranged. Okay. However, they will still remain in one big piece because the strong electrostatic forces of attraction will still hold them together. However, ionic compound, right? They are not malleable. Neither are they ductile. Okay, so question is why? You need to ask yourself, what is the structure of ionic compound? Okay, it's a lattice structure, okay, with oppositely charged ions. So why is it that they are not malleable? Take a look at this video, which will explain. Okay, so in an ionic compound, it's plus and minus, plus and minus. Okay, cation and ion, cation and ion. So if I were to hammer it, okay, so at first it is plus and minus, right? Okay, purple and green, purple and green. If I were to hammer it, okay, this portion here, take a look at where my cursor is. I have purple and purple, green and green. And purple, green and green means like charges. Okay? So I have these like charges, Cl minus and Cl minus, they are beside each other. What will happen to these two ions when they have like charges? They will repel. Okay, so they will repel and then they will start to break into pieces. So if I use a metal and I hammer it, okay, even though they will still slide, But you notice, what is in between the cations? Do you notice? The ones that are in between the cations are my delocalized electrons. So these delocalized electrons, okay, they are still having strong electrostatic forces of attraction. So if I want to see it, zoom in and see, it's still plus, minus, plus, minus, plus, minus, plus, minus. So there is no way I will have plus and plus together, because in between I always have the sea of delocalized electrons. It's always surrounding all cations. So that's why it can mold it into different shapes. So we learned about the electrical conductivity of metals, and because of the sea of delocalized electrons, okay, it can act as mobile charge carriers. Okay, then we also take a look at the different properties: high melting point, boiling point, it is malleable, good conductors of heat and electricity because of the structure. Okay, so this is the end of metals. Okay, so we have finished ionic bonding, covalent bonding, and the last part, metallic bonding. Now remember the metallic bonding because it will be very important for our next topic, which is called metals.